Hey everybody, this is Larry. This is day 26 of the June Leetcode Daily Challenge. Let's get to it. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Count of smaller numbers after self. So you're given an integer numbers, you have to return a new count array. The count array where the number sub I is the number of smaller elements to the right of num sub I. Okay. So there are a couple of canonical solutions to this. It's a studied problem-ish, at least in competitive. I think for example, there's segment trees, there's binary index trees, some things that I talked about earlier, because you can just literally as a query you just think about your patterns, right? You go from right to left, you go, okay, 1, what's more than 0? Or sorry, what's 0 or smaller? None, 0, and then 6, you do what's 5 or smaller, and so forth, dot, 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 right? And of course, you can change that. You can change that into a query from that instance, because you can just get the count of the numbers from 0 to 0, 0 to 5, 0 to 1, 0 to 4, and so forth. So that's how the general idea behind binary index trees and segment tree. But that's of course too high powered. I don't want to mean to scare y'all. I personally don't think segment trees or binary index trees should be on any interviews, though. And I don't even know if it's good if you bring it up on an interview, because then they would ask you about it, and unless you have a very good understanding of it, it just becomes a buzzword, and then they kind of discounted you a little bit. I made that mistake before, not gonna lie, where I'm like, oh yeah, I think this has a solution that uses XXX algorithm, and then they asked about it. I'm like, oh, I guess I wasn't as studied about that algorithm as I thought I would. So then they just think I was BSing. But anyway, and it happens because when you do a lot of problems, there are a lot of situations. But I think a fundamentally easier thing as well, which is to keep a binary, depending on your languages, you could keep a binary tree, and then just as we said before, you just kind of keep inserting and then just search on that binary tree for numbers that are smaller than it. That seems pretty straightforward. In Python, there's a thing called sorted list, and that's what I'm going to use, which has the same idea about the invariant, right? Which is that everything is sorted, and also I guess maybe the probability that the invariant that you want in the data structure is that you can keep on binary search on it, which is why I equivalated to like a set search or something like that, well, maybe not just set, but like a like a tree list type thing, tree map thing in other languages. Anyway, so that's basically all the kind of theory that I'm going to get to. Is there just thinking a second whether there's a linear solution? I don't think there's a linear solution, because that would be funky. Maybe it is, I don't know. I mean, or at least not in the way that people say, because I think sometimes people say linear when they mean when they depend on the range of the universe, which I don't know. I always discount that a little bit. But in any case, I think that's sufficient enough for us to get started. So yeah, can you do things in linear time? I'm still questioning myself. Maybe we can do an upself thinking. But yeah, I think that should be okay. So at least in Python, there's this thing called sorted list. If you get asked about it, I would just say that it's kind of like, is that the actual implementation is actually not this, but in concept, it has the same invariant, even though technically that's also not true if you really look into the implementation and the caveats, because there are some degenerate edge cases. But for the most part, unless you're designing as an adversary, you could get that log n search time. So that or update and search and all that stuff. So now we have a sorted list, and we just kind of go backwards. let's keep track of an answer as well, and you can do it either way. I'm gonna just reverse the list later, so that's why I'm keeping it like this. But then now we just do nums dot. Okay, maybe we can even do nums dot reverse, even though you can do it in the numerator as well, or in the iterator as well. But it's fine in the for each loop. So now for x, we do sl dot bisect left of x, and this is the index that you're given. So these are the numbers that are going to be, so the index will give you the number, the first index that is the number and bigger. So then you just subtract that from the length, right? So n is equal, oops, n is equal, we don't have to, because I think we only use a sphere. And I think that should be good, except for that obviously you have to insert. Is it insert or add? I always forget. And then at the very end you reverse it back and then just return answer. I think that's roughly what I would do. Oh, yeah, okay, that is not quite correct. So we might have to do some debugging. Maybe I mean, they're only really they're like 2 lines of code, so it's kind of hard to debug. But in a sense that, I mean, it's here. So okay, yeah. The smaller one is always a little bit tricky for me, so I'm going to do it another way. What I'm going to do is now, instead, I'm going to do the opposite, which is to negate everything by using the negative, and then I think this should be good. Well, now you do a bisect right, I believe, because you don't want to include the x, and I think that should be good. Maybe this way is a little bit more confusing though. Okay, it's still wrong. Oh, did I run it? I don't know if I ran it. Let's make sure I ran it first before I debug. Made that mistake before. It should be this +1. I am being very awkward, but the idea is right. But what am I doing wrong? Okay, -1, that's fine. And the negative, I mean, I know why this is wrong. It's because it tries to go to the next index. So this should be, that's the number of numbers that are smaller than it, right? Why is this inserting at -1, -6 would have 0. Oh, I see. So this is that. Okay. I just have to think it through. I think I was just sloppy and trying to be quick. But the idea here is that, you know, if you think it through, then this will insert at the beginning. So then now you have to take the length of the thing to kind of to remove it, to count the stuff that's to the left of it. So if you have confusion about this, I recommend you draw it out. I kind of visualized it in my head, but let's give it a submit. Hopefully I'm right, and it looks good. Yeah. Can I upsolve this? No, I don't. I mean, I'm thinking whether there is any like mono stack or things that I can take advantage of, but I don't think so, because then now, for example, if you, yeah, I don't think so. I think you need to know all the data, but I could be wrong, so leave it in the comments, or maybe we could check it out later. But yeah, but that's basically the idea. I actually think the way that I did is a little bit yucky. Might need to explain this a little bit, but the idea, I think the idea is still like binary search, and then you know you you kind of count the index on the left or on the right, and that should be good. It's just that maybe I don't know why do I need the negative? Is this? Maybe I was just kind of being sloppy. Maybe I didn't need to. I think I confused myself a little bit. Yeah, I think this is good, and I think I recommend this instead. So I hope you stayed until now. But basically, this is just okay. Get the index on which is inserted. So then everything to the left of that is going to that be smaller, and then you just add it. And then why do you insert the index, right? Well, this is a little bit confusing, and is because that you basically add 1 because to the left of the index, for example, if you're inserting an index 5, that means there are 5 numbers to the left of it, which is 0, 1, 2, 3, 4, right? So that's basically the idea, even though it looks a little bit confusing as to why that's the answer. But yeah, and as we said, the bisecting is going to be log n, the add is going to be log n to this sorted list, which is, yeah, let's pretend it's a binary tree or some assorted binary tree or a binary search tree. And yeah, so this is log n, and we have O of n items, so this is going to be O of n log n. In terms of space, we do use an extra space. This is O of n, this is O of n, which is output sensitive anyway. So yeah, that's going to be the lower bound. That's all I have for this problem. I don't know if this is that interesting. If you really want to practice using binary index tree or segment tree, this may be a good problem to do it, because at least if you want to focus on implementing those things from scratch, because if you just copy and paste them, then this is a for loop and it's really silly. But if you want, build your muscle memory, this is probably a good problem to kind of do that. That's all I have, I think. So yeah. I hope y'all have a great weekend. The Leetcode contest this week, and a couple of them. I hope y'all do well, or just hang out, come to Discord, let me know what you think. Summer's here, yay! And also happy Pride weekend for those of you celebrating. I mean, I know it's a month, but it's New York, and it's a little bit happening here. Anyway, that's all I have. Stay good, stay cool, stay healthy, and to good mental health. Bye bye.